Hello and welcome to another worked example with Dr. Schleif. As you can see, we're dealing with some projectile motion. Calculate the horizontal component of U. If U is 12 meters per second and it's launched at an angle of 50 degrees above horizontal. So we want this component here, the horizontal component, and because that's adjacent to the angle in question, it's the cosine of the angle times 12 meters per second. That's going to get you to that solution. So everybody with a calculator knows that the cosine of 50 times 12 is 7.7 meters per second. Moving right along. What about the vertical component? All right, so let's kind of, yeah, so just rewind the video a little bit and you'll be able to pause it there and view it at your leisure. If you're in class right now, that's not really helpful to you. So just be sure to get on the Dr. Schleif notification squad for all your physics calculating needs. So the sine of 50 degrees times 12 is going to be the vertical component of that. Question? Yeah, I have it too, but I had it long ago, well before you did. Well, what did you get? Yep, 9.2, let's say. 7.7 for the horizontal, 9.2 for the vertical. Moving right along. Show that the maximum height reached by the ball is 4.3 meters. All right, so let's remind ourselves what we had. We had a vector like this, 12 meters per second, an angle of 50, and we just calculated this component was 9.2, and we calculated this component here was 7.7. The other way to calculate this one would have been to use Pythagoras' theorem, right? We could have said, well, this quantity squared plus some quantity, right? We don't know it, squared equals 12 squared since we're given the hypotenuse, and we could have solved it using Pythagoras' theorem. So we're trying to show that the maximum height is 4.3. So we kind of sketch it out the way we were doing these calculations before. Let's see, we want this vector right here, the height. All right, what can we do for this one? Well, what do we know about sort of that point in its motion? Exactly, everybody was silent because you know that the velocity goes to 0 at that point. So like the null set, 0, I'm not going to say anything. All right, and then we've got testing. Here, take care of this. Yep. All right, so if we know the velocity goes to 0 at that point, we're trying to solve for the displacement. We could maybe use the equation of motion like v squared equals u squared plus 2as, and then solve for the displacement here. So we'd say an object that is launched at 9.2 meters per second, that's going to be affected by gravity now. So gravity opposes that, so we're going to make it negative 9.81, and then solve for s here. And again, we know that at the top of its flight, the very place where we want to kind of know or show that the height is 4.3 is 0 there. So this is an equation of motion that doesn't contain time, right? It's the one equation that doesn't contain the time term. But we could figure out how much time it's going to take to get to maximum height the way we were doing our projectile motion calculations the other day. So v equals u plus at. And we could say something that's launched at 9.2 is going to be airborne for how long before it reaches its maximum height, right? We could solve this equation right here for time. And then knowing the time, we could use our shortcut h equals 1/2 gt squared. So we'll actually solve it both ways. We'll solve it this way and we'll get the displacement, the height, should be 4.3. And then we'll figure out the time that it takes to get to maximum height and plug it in here and show that the answers agree, okay? So let's solve this one first. 9.2 squared is 84.64. So we'll subtract that from both sides. So negative 84.64 on that side equals 9.81 times 2 is 19.62. And then S is the displacement we're solving for. We call it h to be consistent, whatever. All right, so if we divide each side by, well, that's going to be negative, right? So divide by negative 19.62. So I have 84.64 divided by 19.62. And indeed, this gives a displacement of 4.31 meters, or 4.3 meters, like it says we should get. So finding the right equation of motion that just solves for the thing you want to know based on everything else that's given, that's kind of nice. But this is kind of what we're used to dealing with projectiles. So maybe you say, well, I want to figure out the time to maximum height, you know, and this is the way that we had been solving that. So we subtract the initial velocity in the y direction from both sides, and then divide both sides by the acceleration due to gravity. So we're just taking that initial component divided by 9.81. So 9.2 divided by 9.81 is 0.937. So the time is 0.937 seconds. If we square that and multiply it by 1/2 g, 9.81 for g, we should hopefully agree. So I got this 0.937 seconds in my calculator, square that, times 9.81 times 1/2. And sure enough, you get the same answer, 4.31 or 4.3 meters. So that just kind of goes to show that there's many paths to the same correct solution. Maybe you want to know what the time is though, right? So you solve it, you know, for time and then plug it back into another equation. Either way works. The next part says determine the magnitude of the displacement PQ. So if we go back up to the figure, we'll remind ourselves that P is the initial sort of launch point and Q is where it's at the top of its flight. Let's clean this up a bit. It wants the straight line sort of displacement from there to there. Okay, like if we were looking from the ground at point P up to where it's going to be at the maximum sort of height, what is that sort of distance there, that displacement? Well, we already know that this right here is 4.3. And if we could somehow calculate the horizontal displacement, then we would have a triangle that we could use Pythagoras' theorem with. Does anybody know a fancy word for horizontal displacement? Range is incorrect. It's not fancy. It's not fancy at all. It's just a way to say horizontal displacement. Horizontal displacement actually sounds fancier if you think about it. Okay, but range we know is Vxt. And Vx we calculated way back when to be 7.7 meters per second, you may recall. And the time that it took to get to point Q, we did calculate a moment ago, 0.937 seconds, right? So that did come in handy. So we're calculating, remember, the halfway range. We said that this was a method that we could have used in our own projectile motion calculations, calculating the halfway range and then doubling that to get the full range rather than doubling the time to get the total time airborne. So the range equation works everywhere. If we want to know the halfway range, we just plug in the time to that point. So we've got 0.937 seconds times 7.7 meters per second, which means this thing was going to be 7.2 meters downrange. We already showed that the height was 4.3 meters, and this is our path to getting this displacement vector, right? Just using Pythagoras' theorem with this triangle here. So we're going to have our answer, let's call it R for resultant. Resultant squared equals 4.3 squared plus 7.2 squared. I still have that 7.2 in my calculator, so I'll square it. And I'll add 4.3 squared. They give me like 70.54, but don't report that as your answer, because you still got to take the square root. And so I'm getting a displacement here, PQ, of 8.4 meters. So that's the magnitude of the displacement PQ. That's a total of 8 marks. If you're using this resource, cienotes.com, or some previous ACE physics papers, then you can conveniently change this question paper to MS mark scheme. And we're going to check the answers now real quick. So everybody remember what we just did. All right, so here are the solutions. And we were doing number 2 there. And we can see that the horizontal component was 7.7. The vertical component was 9.2. They show sort of different methods. Here's an energy argument where they use potential and kinetic energy to solve the same thing. We didn't talk about that. This is yet another equation for like projectiles and solving for the range or something like that. I think so. We use this way over here. Any way you do it, you get 4.3. It says alternative methods using time, right? We kind of solved it that way too. So lots of different ways that you could have shown that the height was 4.3. And then 8.4 meters was our final displacement, and we get that by using Pythagoras' theorem. This has been another worked example with Dr. Schleif. Still living the physics life. See you next time.